In the earlier class, we saw discuss about the inertial frames and the non-inertial frames. Okay, so any frame which is moving at a constant velocity, all those frames are inertial frames. So in an inertial frame, there won't be any force acting on it because there won't be any acceleration. Correct? Any accelerating frames, any reference frame which is accelerating, that means it's a non-inertial frame. Okay, for every acceleration, anything is acceleration. Okay, there will be some type of force will be there. Okay, so maybe your gravitational force. Okay, and we see, because we normally in a day-to-day life, we don't see anything in a constant motion. We see everything is in a, have some sort of acceleration. Even the motion of Earth is orbiting around the sun, right? Is it a straight velocity? It's making a elliptical orbit, right? So of course, elliptical orbit will have some force there. So there is nothing like in a you have to go into absolutely zero gravity where there is no in the space, no gravity. There if you try to push a rocket or something, there you can see that rocket will move with a constant velocity. Okay, so then that's what your inertial frame. Okay, so the so what I was saying is, so there is in nature all inertial frames. All the frames in general, the frames are not inertial. They all are non-inertial because there is some force acting on it. The frames are getting accelerated. All those things. So what Newton's law says is, for any acceleration, there has to be a force. So if any frame is getting accelerated, there will be a force acting on it. It can be either pseudo force. We will see that all those things in the upcoming class. There's some sort of force is there. So force is something kind of a fundamental quantity which causes the frames to accelerate. Okay, and universe, as I told you, everything is non-inertial. Everything is accelerating. Your spin of Earth is a spinning. For a short time, I can say I'm having maybe a linear velocity. But over 124 hours, I'm making a complete rotation, right? So even that every motion is a non-inertial frame because there's a thing like a linear velocity or moving at a constant velocity. Fine. So then force is something a fundamental quantity. So now, what are the types of force we see? Because when I say types of force, then you say, man, you can have plenty of forces. You kick a person, kick a ball, that's a force. You fire a bullet, that's a force. Because the bullet is, initially the bullet was at rest, it's moving with the velocity. When you kick a ball, the ball was at rest, the force is there. You drop a ball, it was at rest, now there's the acceleration. Okay, there's the change in motion. Okay, there's from rest to having some velocity or some velocity to rest. Okay, so there is a force acting. Something is moving, you're going to stop. So velocity everywhere you see. So all this, there's nothing like a constant velocity. Everywhere there's a change in velocity, so there is a force. So now there are different types of force you see. Now, is it possible to find all these forces are basically a single force? Okay, what you call the unification of force. It's a manifestation of a single force which gives rise to different forms of force what we are seeing in our day-to-day life or even in the planetary motions. Okay, so when you see that, so what happens is it is not a single force, though it is advanced theory how to unify all the force into a single force. They were not able to succeed it till now. Okay, with the string theory and they were able to say that they are able to unify all the forces. That's different. So what I'm not going into those details of it. For your class, what you see is certain types of force, all types of force what you see in the nature, in the universe, can be categorized into 4 different forms. These force belongs to one of these 4 different types of force. What is the type? I am going to write. So the force, basically, it divides into 4 different. In the universe, there are only basically 4 types of fundamental forces. One is gravitational force. What is the gravitational force? You know that, right? Yeah. Gravitational force. Gravitational. Okay, let me write it. Gravitational. And the second one is Electromagnetic. I'll come to it. You know electromagnetic. And this is interesting. I'll tell you why it is interesting. Magnetic. It's a unified. Earlier people, because electricity also can create a force, right? What? Electron and electron repels each other. Electron and positron. A positive charge and negative charge attract each other. Okay, you have seen it. You taken the scale and rub in the paper and put of paper, they all attract each other. That force is what? That's not a gravitational force. It's not a scale's gravity is attracting the gravity, the scale's mass is attracting the mass of the paper. There's a force acting. The paper is being, you got it, you did the experiment, right? Take the scale and rub in your hair, oily hair, and then you put up, the papers will stuck up, right? So there is a force acting. Static electricity. That is okay. That's what you call it. Because there's a charge. By rubbing, you created a charge, and that charge is attracting. So this is electric force. Okay, and similarly, you can do it for a magnet also. Correct. So, but it's not magnet. You rub it on the hair, and then you tap. Magnet, you keep it, it sticks. Okay. So ideally, what you think, magnetic force is different, and the electric force is different. Okay. Later on, it was the Faraday. You see the law. Okay. When you pass electric current through a coil, it becomes a magnet, electromagnet. Okay, so and when you change a magnetic field on a coil, electric current is being produced. So this says that your magnetic field, electricity, they are not an independent quantity; they are coupled. So that's why I have already unified electricity and magnetism. So that is what you call as an electromagnetic force. Okay, that property. So either it's a magnet or it is a electric charge force. They all can be unified into one single force, which we call as electromagnetic force. And now this is the two force we see very commonly. And the next two force, it's very, it is not very commonly people know it. So if you remember, what is how do you find the structure of an atom? There is a nucleus. Okay, and there are electrons revolving around it, whatever the orbitals you have read it in your last year chemistry class also. Now, what is there in the nucleus? Can you tell me?
Electrons and protons.
Nucleus.
Protons and neutrons.
Protons and neutrons. Whether the protons are, all protons are positive or negative? Protons are?
Protons are neutral.
Protons are neutral, neutrons are neutral.
Protons are positive.
Protons are positive. Okay. Now, your electromagnetic theory says the like charges repel, electron repel. So the nucleus, the proton also has to repel. But in the nucleus you see in the nature, nucleus, all the protons are bound together. Even though they are having a same charge, they are bound together. So there is some force which is binding the protons into the nucleus. Correct? So that's what the nuclear force. Okay, that you don't see it common. Because whatever you deal, everything is in atomic electron, that orbital, that force is only you see. Okay, you never go into the nuclear unless until you go for a nuclear reaction, like an explosion, nuclear explosion, or in a sun, star, all those things you find out. So these forces, okay, there are two types of forces. I will come to that. Okay, so one force is your strong nuclear force, strong interaction they call it. Yeah, okay, they call reaction force also. Strong nuclear force. Strong nuclear force. And the another one is weak. Okay, as I said, it's a strong. Then there will be a weak nuclear force also. I will explain you why it's a weak nuclear force. Okay, so weak nuclear force. Weak nuclear force. So, and what they found in the universe, every force, whatever the force you are dealing, they all can be categorized into this four. There is nothing other than this exists. All forces are basically derived, whatever the force. You drop a ball, you take a water tank. When you open the water tank, the water flows down. Okay, and why the water flows down? Okay, you hit a nail on a wood. Okay, so there is a force you are applying. Every force, whatever the force you deal in your life or in the universe, wherever you see any motions and everything, they all come under these four types of forces only.
But what about if I hit a nail,
correct,
that type of force, which one will it come under?
Yes, now think, tell me. So now, the nail is made up of what?
Metal.
Metal. Okay, metal, of course. Nail is metal, but metal is made up of what? What is the subatomic level if you go.
Atoms.
The atoms and electrons. Okay. So body is rigid because of your structure of the atoms, and you have studied about ionic bond, okay, covalent bond and all you have studied. Am I right? So these bonds make them hard. Strong bonds, you can break it up. Okay. So now you have another material of same bond. When you try to press it, hit it, what are you trying to do? You are trying to break the bond. Okay. Okay. So what force is acting there, which is stopping it? If the atoms are all free, you wouldn't have stopped any force. Am I right? So the force,
Intermolecular force.
yes, not nuclear, electromagnetic, because you are not going to hit the nucleus.
No, intermolecular forces. But
Correct. That will be what? Electromagnetic.
Okay.
Intermolecular, the attraction, all electric, positive and negative charge. You saw the covalent. Am I right? Covalent bond, ionic bond. You saw in your earlier chemistry class. These are all basically what? Electromagnetic. All this force, whatever we deal on our day-to-day life, they all are mostly they are electromagnetic. Okay, pull a rubber band. There's a force. When you leave, it hits. This is all electromagnetic. These all are basically the way the bonding is there. It's a carbon chain, or means you are an organic chemistry and all you have done it. Okay, so everything you study, the elasticity, durability, or what is it?
Durability.
Ductility or something like you heard it in the chemistry class. So these all these properties, everything you need a force. Okay, and that force, everything has an. If you see deep inside, they all are basically electromagnetic in nature because they are the binding between the molecules. And the molecules are bound by the electromagnetic. When you apply a force, you're basically deforming this binding. Okay, that means what? That force means you are already applying a force with another molecular chain, and that you are hitting it. This is hitting. If this is a weaker one, it moves off. It breaks up. So ultimately, all those forces, whatever you see in your nature, because humans, anything on the earth or even in the universe, they all are made up of because they are basically charged particles, electron, neutrons, and neutrons also, electrons, protons, and neutrons. Okay, normally we don't see about protons in the atomic magnetic. What you will see is only about the electrons only. Okay, so this is what we call as an electromagnetic force. Another force is what is a gravitational force. And interestingly, among these four forces, the weakest of all the force is a gravitational force. Okay, it is the weakest, but the entire universe is bound by this force. Okay, this is the weakest of all the force. Okay, and it is not the charge of the sun and the charge of the earth which is making it to spin around. It is the mass of the sun and the mass of the earth. If there is a two mass, the only force acts between two neutral bodies is the gravitational force. Okay, so and you must have studied the gravitational force, right? What is that? Tell me, what is the gravitational force formula? You know that?
G-M-M by
Correct. What is the gravitational force? You have studied in your F force. F is a vector?
It's a vector. No, it's a vector, right?
Correct.
It's accelerated.
Vector, yes.
Mass,
G, mass is a vector?
mass is a scalar.
Correct. M1, M2 between two bodies divided by
R square.
R square. Okay. So now R square. R square is basically a scalar. You take a mod of it. Left hand side is a vector. So right hand side also has to be vector.
G.
G is a constant, of course, not a vector. So tell me where the force will act. Take a two body. What is the R? R is the distance between the body. So what you have, you are having two bodies, M1 and M2, separated by a distance R. Okay, so can you tell me where will be the direction of the force?
The higher, more body with the higher
Whatever,
mass.
it's along R.
Okay.
Am I right? So it's along R. So this will be an unit vector along the direction of R. Oh, sorry. Unit vector along the direction of R. Am I right? Or if you want to write a unit vector, ideally the point is U vector R vector divided by R magnitude. Am I right? Or I will call it as a, maybe you can call U of R cap. So if you attract, this is a, okay, there's a symbol generally people use. For an attractive force, they use negative sign.
Okay.
Because they both are opposite in the, okay, they're also opposite. Okay, attractive force is usually represented by a negative one. Okay, and repulsive force is positive. Okay. So this is the gravitational force, and the gravitational force is very commonly we all face the gravitational force. Can you tell me what is the, okay, let us do that. So for example, okay, why are we stuck to Earth? Gravitational force. So can we calculate the means what is the gravitational force acting on me? Okay, so what am I going to do? Suppose the gravitational force acting on me, F, will be, well, let me do the magnitude of the force. Why I am going to take the, okay, I am going to do the magnitude of the force. That be what? G, mass of the Earth, and my mass divided by,
Distance between the center of the.
that should be what? The radius of the Earth. Because, okay, my center of mass may be here. You stand here or stand on the stool. It doesn't matter for it because the radius is so large. So what I will put a radius of the Earth whole square. Okay, and this force, which is due to gravity, which is acting on me, we call it as a weight. This is what we call as a weight, and we write this as mg. It is mg. Okay, now can you tell me what is g from here?
G, capital G, capital M by R square.
R square. So now let us try to calculate what is g m by r square. Can you tell me what is a, you remember the constant values? G? 6.67 into 10 to the power of minus 11. That is a gravitational constant. The mass of the Earth is 6 into 10 to the power of 24 kilogram. Okay. And the radius is 6.4 into 10 to the power of 6 meters whole square in CGS. Okay.
So,
If you do it, can you do it? If you do it, what will you get? Tell me. So let us take the powers and all separately. Okay. So how to do in such calculation is,
we can separate the powers. And
yeah, correct. So what you do is, so I am going to write G is equal to 6.67 into 6 divided by 6.4 square, right? So I write 6.4 into 6.4. Okay. So typically into 10 to the power of
24
minus 11.
24 minus 7, right?
Yeah, correct. So 10 to the power of 24 minus 11
Divided by 12.
Divided by 10 to the power of 12.
12.
Okay, so that will be minus 12. Am I right? So tell me how much it is?
10, right?
23. Yeah, this is 23. 24 minus 23. This is going to give you us into 10. Correct? So you can typically say they all are same. 6.676, 6.6, all can cancel. So typically it goes as to be 1 into 10 to 10. Correct? So that's what? 10. Okay, if you put exact calculation, exact value, what you get is 9.8 meter. Okay, that's 9.8. Yeah, 9 is the gravitational acceleration due to gravity. Okay, meter per second square. You got it? So this is how you can do. Fine. So this is what. So the gravitational force is the one which is responsible for the weight we feel on the Earth. Okay, and this weight you're going to feel different for different planets on the moon because the mass of the planet will be different and the radius also going to be different. That's why you experience different weight in the different planets or in the satellite moons. Okay, fine. So this is what we all about your gravitational force. And now there's one of the interesting thing you can see. Okay, so what the gravitational force is, see, is there any range for the gravitational force? Means it will not attract beyond certain period, certain distance? No. Why? It becomes weaker and weaker. As R becomes larger and larger, the force becomes weaker and weaker. Okay, if you for the force to make it 0, R has to become infinity. Okay, so it is an infinite force. The gravitational force remains at far distance also. Okay, it becomes very weaker. So that's why I said in the universe, in the space, there, if you go in no gravity space, there you can prove the equation, Newton's laws of motion. Okay, but there is nothing like that, because your gravitational force is universe. It is everywhere. Only its intensity is going to become lesser, smaller and smaller. One way you can do is you can cancel the force. If there are 2-3 gravitational force, opposite forces, that we will see the next problem is there. We will see that there can net effective force can made to be 0. So that's how you can do it. So okay. So this is all about your gravitational force. Now, okay, tell me one thing. So of course, what the gravitational force says is means any two body having a mass is going to attract each other. Okay, so and that means even I should be attracted to the wall, the board, or with you. Everyone has to be attracted, but we are not getting attracted. Can you tell me why?
The difference in mass.
Okay, that's what they have done an example. There's one example in the book. You can do that. They took what is the gravitational force between two sumo wrestlers, put a 300 kg. You find out the gravitational force and see how much that force is comparable with your force between you and the earth. Okay, between you and the earth is so strong. Okay, so that it doesn't means you really don't get the attraction. If you want to put it in a very simple way, you must have done it, and you must have seen it also. You take a big powerful magnet, okay, and you put small 2 magnets over it. Will these magnets attract each other? No. Okay, these magnets will remain even though you put whatever. It doesn't matter. Because the point is, because this attraction is so strong, this attraction is nullified. I mean, it doesn't matter. It's not that strong as this one. So what matters is, and then you must have seen, by pushing the hand, you can push over the magnet easily. But the moment you want to try to raise it, it attracts. Correct? This is exactly how the earth and the people are moving. We are on the surface, we are moving around. Okay? The moment if you want to raise up, then the attractive force of the earth will come up. Okay? So this is what the gravitational force is. Okay? This sumo thing is in the book. You can do it by yourself. You can find out how much the gravitational force difference between two sumo wrestlers and the earth and the sumo wrestler. Okay, so this is all about the gravitational force. And now comes the electromagnetic force. I said the gravitational force is the weakest force. Am I right? And can you tell me a simple example? From the electromagnetic force, I can say, but just by the data, whatever you're thinking, you can say why I say the gravitational force is weaker.
Like in the last example, if we take while in Earth, if we take 2 magnets, they will still attract each other even after being under gravitational force.
Correct. That's also right. That's okay. That's right. There was a simple example. I take 2 electrons. Okay. The electrons have mass. The electrons have charge. So, because they have a charge, they are going to experience the electromagnetic force. Because they are going to have a mass, they are going to experience a gravitational force. Gravitational force, attractive force or repulsive force? Attractive force. So, if the gravitational force is stronger, these 2 electrons would have stuck together. Correct? Because that is very stronger. Electromagnetic is not that powerful. The 2 electrons are not able to stick to each other. They are repelling it because your gravitational force is weaker, whereas your electromagnetic force is stronger. You got it? Huh? So that's a simple example to say that why electromagnetic forces are stronger and gravitational forces are weaker. Okay, now coming down to electromagnetic force, as I told you, initially it was thought to be different, electrical force and the magnetic force. When you rub a scale with a hair and attract the static electricity, that force and the force caused by 2 magnets, they are thought to be different until Faraday proved they both all to be same. Okay, so you have done that, you read about it in your 10th standard, right? So you can, from the magnetism, you can create electricity. From electricity, you can create magnetism. They're basically one and the same. Not one and the same. You can combine them both. You can unify them force. Their force are basically some other way. They all are connected. So that I call them as an electromagnetic force. Okay. So, and this is electromagnetic force. And that is the reason, your atomic structure, your molecule, whatever you're writing, I'm writing on the pen, okay, and everything, wherever I'm doing, all our day-to-day life thing, what we are seeing is basically the electromagnetic force. The ink, why it is stuck up to the board. When I rub off with the duster, the ink comes off. Everything there's a force acting on it. All these forces comes under, they're not gravitational force. The ink is not stuck by the gravitational force of the board. Am I right? That's the electromagnetic force. So everywhere, whatever normal day-to-day life, whatever we see, that's basically an electromagnetic force. Okay? Clear? So that's what they have written. Yeah, there's something more they have written. Yeah, actually, because after it was basically Faraday's demonstration and the it's the Maxwell's equations. You will study when you were possibly in a BSc. We'll study about the Maxwell's equation where it says electric and magnetic field force can be unified under a single theory. Okay, and that's what we call electromagnetism. So that's what is this theory. These forces are stronger than the gravitational force, as I explained you. Our life is practically governed by these forces. Am I right? So majority of the forces experienced in our daily life, such as force of friction, normal reaction, tension in strings, collision forces, elastic forces, viscosity, the fluid, etc. all are EM in nature. So short form is electromagnetic. They call EM force, electromagnetic nature. Okay. Under the action of these forces, there is a deformation of objects. Okay. When you break object, basically you're breaking the bonds. When you deform, you're basically realigning the bonds. Okay. So there's a deformation object that changes the intermolecular distances, thereby resulting into reaction forces. Got it? So this is whatever in the day-to-day life, whatever we see is our electromagnetic forces. Gravitational force is the force which is responsible for the entire universe structure. Orbit of planets around the sun, everything. Okay, everything, your galaxy formations, everything. One of the main force is the gravitational force. Okay, and then comes the next two interesting forces, which normally we never see in our life. Okay, so that is what? Nuclear forces. That is strong nuclear force. I said the strong nuclear force is simple. How can you, and this is extremely strong. Am I right? Will this be stronger than electromagnetic? Why?
Because it holds the
protons together. Electromagnetic force will not let my protons to come close to each other. Okay, but this clubs a proton together. Now you tell me this electromagnetic force. Okay, I forgot the electromagnetic force. Is it a short range force or it's a long range?
It's a short range.
It's a long range. Okay, because actually, ideally that also will goes to be infinite because charge, two charge. You had studied about the Coulomb's force formula. Two charges force between two electrical charges, Q1, Q2 by R square. Something like that, similar to your gravitational force, it will come up. So that's also this is also a long range force. Okay, it can go, but only thing, it decays very fast as it goes to long range, much faster than your gravitational. So that's why as you go far away, the gravitational force will dominate. Okay. So now coming to this nuclear force. Okay, I said about the strong nuclear force because that's how your what you call typically the protons and neutrons are called as the nucleons. How the nucleons are bound together. Okay, that's a force by which you don't have to really bother about it because you will study in the reactors. But one thing you know, of course, the protons and protons are not repelling each other and breaking apart. They are bound into one small nucleus. Okay, so that means there is a force which is attracting even the protons and neutrons and all. So that's what your nuclear force. Okay, but only thing is this nuclear force. This is the strongest of all the forces. As you can see, because it's much dominating than your electromagnetic force. Electromagnetic is stronger than a gravitational. Okay, and the strong nuclear force is stronger than your electromagnetic also. Okay, and the point is, but the interesting thing is this nuclear, strong nuclear force is not a long range force like electromagnetic and gravitation. If that is the case, why am I saying it's not long range? If your nuclear forces are long range, you have two atoms. Can the atoms remain be stable? Think over. What is the structure of atom? You have a nucleus and the orbitals of electrons. Am I right? So whatever you have. There's another nucleus. Okay, and there's another orbits of electrons. Okay, whatever you write out. And what I'm saying is the protons and neutrons inside the nucleus, they are all bound by a nuclear force. So this is what the force we are calling it as a strong nuclear force. If this strong force is a long range, that means this would have attracted these protons also. Okay, protons, all the protons here, and all the protons would have stuck each other. Am I right? You'd keep all the atoms will become a single whole earth will become a single big nucleus atoms. Okay, so it doesn't happen. That itself says, so this nuclear force, though it is a very strong force, it's a very strong force because it's overcoming the electromagnetic repulsion between the protons. And they're binding. They're very strong force, but there has to be a very short range force. If they won't be infinite. Okay, typically this force, the range will be 10 to the power of minus 14 meter. It's so short within nucleus size. Okay, so this is what how your protons and neutrons are clubbed, stuck into a small nucleus. So that force is what you call as your strong nuclear force. Okay, and that is a short range force. You understood why it has to be short range. Okay, now coming, what is this? Okay, when I say weak nuclear, it sounds that it is a very weak force. It is not actually weak. This can be strong. This is much stronger than your gravitational force. Compared to strong nuclear force, it's a weak nuclear force. Okay, what it says is, suppose there is something, what the people have observed is something called as a radioactive decay. That's how it gave rise to this first thing came out to be what is a weak nuclear force. Radioactive decay. What it says is, you have a nucleus. Suppose for example, you must have done the carbon dating, radiocarbon dating. Okay, you have seen the people use radiocarbon dating to find out the age of a certain old. So that's how they clear most of the mysteries, especially these religious mysteries and all. Okay, they will say that belongs to the period of Jesus or something, but when they do the radiocarbon dating, it belongs to 100 years back. Okay, okay, so okay, that's a fun part. But actually, why? What is important is, now you see, I'm telling this nucleus is a very strong force, short range force. Okay, that means, and this attractive force between the nucleons. It shouldn't leave anything. Okay, but that is not true. There is something called as radioactive decay. So what happened? A nucleon can be a proton or a neutron. A proton or neutron can undergo something called as a beta decay. Okay, what's called as a beta. Beta is typically called for electron. Okay, so what happened? What you see is a proton. Okay, a proton will break up into a neutron and a positron we call, and there's something called as neutron. I will come to it. Similarly, a neutron, okay, will become a proton, and by releasing an electron and some neutrino. Okay, so we'll come. So what it says is, in the nucleon, even though these nucleons are attracted to each other, this nucleon suddenly changes from a proton to neutron, or neutron to proton. Okay, what it does is, suppose a neutron is there, the neutron will release an electron, negative charge. So in a neutron is a neutral. When you take out an electron, it becomes what? Positive, na? Positron. Okay, because from a neutral you take out a negative charge, then this becomes a positive charge. Okay, and similarly from the proton, you take out a positive charge,
becomes a neutron.
Neutron. That's how it becomes a neutron. Okay, it's a simple way. It's a very silly way of explaining, but no, none of the nuclear physicists will accept the way I'm explaining. But it's to remember it. Okay, so typically what happens? A neutron becomes a proton by releasing an electron. Similarly, a proton becomes a neutron by releasing a positron. So now what they call something is called the energy balance. Okay, you will study in the higher class. This equation cannot be balanced in energy. Okay, so for this equation, this process to happen, a neutron becoming a proton becoming a neutron, you need one more body, one more, what they call the boson. You will study about it later on. So one more particle to be emitted, and that particle is called as your neutrino. Okay, so this is an example they given in your book. So I won't go in more detail into it. So these types of force. So there is some force, even though it's a strong force, something is happening. The protons are converting into neutrons are converting into, and that is not as strong as nuclear, because of course that's why the particle is escaping out. So that force is called as your weak nuclear force. You understood? Okay, so, and let me read this thing in your book. So this is the interaction, weak one I'm saying. This range is much shorter. This range is typically 10 to the power of 100 times smaller than this, 10 to the power minus 16 meter. This happens within the nucleons. A nucleon becomes proton and a proton or a neutron. Okay, get changes. So this one. This is the strongest force that binds the nucleons together inside a nucleus. Though strongest, it's a short range. It has to be short range. Okay, otherwise you don't find it in nature. You don't find all many atoms and molecules. They all become into a single nucleus. Okay, short range. Therefore, this is very strong attractive force and is charge independent. Of course, it's a charge independent. Otherwise, proton will repel each other. Okay, it doesn't matter. It's a proton or neutron. They attract to each other. Okay, this is what your strong nuclear force. And the weak nuclear force, okay, this is the interaction between subatomic particles. That is what neutrons and protons, subatomic. That is responsible for the radioactive decay of atoms. In particular, beta emission. This is what is called as a beta emission. Okay, beta emission. The weak nuclear force is not as weak as gravitational, but much weaker than the strong nuclear and the EM force. Okay, that's weaker than these two, but not as weak as your gravitational force. Okay, the range of weak nuclear force is exceedingly small. That is typically 10 to the power of minus 16 meter. Okay. Well, let me read about this another one. The weak. Okay, and that's what carbon dating. See what happened. Actually, one of the very common. What do they do in a carbon is, see, all living beings, till then beings which are living, they keep absorbing, accumulating carbon. Well, because everything, whatever the food we eat, everything is hydrocarbons. Am I right? So hydrocarbon chain. We organic things only we eat. Even the plants, everything. They all are organic. So when they live, they accumulate a lot of carbon. So the carbon, the abundant carbon comes in two types. One is your C12. You remember that? Atomic number 6, whatever you call it has a, atomic mass is 12. Okay. And there's another one type of carbon, there's isotope of a carbon, which is C13. Okay, so what happens here the nucleus of this carbon, actually they both are relatively stable. This is more stable, but it's relatively stable, but it less stable than that. Okay, what happens? So here what happens, your nucleus contains 6 protons and 6 neutrons. Here, the nucleus contains 6 protons and 7 neutrons. That's why atomic number becomes 13. Okay, here what happened? This contains 6 protons plus 6 neutrons. That's why it becomes 12. Here it contains 6 proton plus 7 neutron. Okay, so now this is unstable. So this reaction, this undergoes a weak nuclear reaction. So what happened? This one extra neutron, sometimes this neutron will become a proton and become 6 proton. So when it becomes 6, it becomes nitrogen. Okay, 7 protons and okay, you can become 7 protons. When the a number becomes 7, it becomes nitrogen. So then what happened? Eventually, it becomes nitrogen. So all living organisms, we know what is the fraction of carbon 12 and carbon 13 in the nature. Whatever I am eating, I know I must have accumulated this much of carbon 12, certain fraction of carbon 12 and certain fraction of carbon 13. Now if I die, then what happened? I am not going to accumulate any more carbon. So this carbon 13 will undergo slowly this weak interaction, becomes a nitrogen. So this carbon 13 number is going to go down in my body. Okay, now I know what is the time typically takes for this beta decay. So now I can actually count some body, something which is dead for long. A lot of carbon 13 would have been gone. For something is nearby, means recently died, the carbon 13 number will be much higher. So the percentage of carbon 13 isotope in that body is going to tell you the age of the body. You got it? So that's what you call as a radiocarbon dating. Okay, and what they say is the radioactive isotope C13 is converted into N14. Yeah, this becomes N14. Yeah, because it becomes 7 and becomes N14. Okay. Yeah, basically because one proton, so one neutron will get converted into a proton. Okay, therefore it becomes 7. Okay, N14, in which a neutron is converted into a proton. Correct? This property is used in a carbon dating to determine the age of the sample. I said you how. Okay. In a radioactive beta decay, the nucleus emits an electron. This I told. In a radioactive beta decay, the nucleus emits an electron or a positron. This is called as positron. And an uncharged particle called as neutrino. Okay. There are two types of beta decay. One is beta plus and the beta minus. Okay. Sorry, beta plus and beta minus. Okay. During the beta plus decay, a proton is converted into a neutron. Correct? And during a beta minus decay, a neutron is converted into a proton accompanied by an electron emission. Here it is accompanied by an positron emission. Along with a neutrino also will come. Okay. Another more interesting illustration of the weak forces. Yeah, this is interesting. For the fusion reaction in the core of the sun. The sun, there are a lot of nuclear reaction happens. Okay. And there are these weak forces. There also this conversion of these things, proton to neutron, neutron to proton, will all happen. How do you know such conversion is happening? Because this conversion will emit a particle that is called as a neutrino. So if sun is a strong emitter of neutrino, that means some of this weak interaction is going on in the sun. And of course, sun is a strong emitter of neutrino. Okay. Okay, so that's why you know this neutrino facilities are coming up, observatories. Okay. So you can see in the news. Another most interesting was the fusion reaction in the core of the sun. During this, protons are converted into neutrons and a neutrino is emitted due to energy balance. I told you, na? This has to happen because only energy balance will happen. Okay, energy balance. In general, emission of a neutrino is the evidence that there is a conversion of proton into a neutron or neutron into a proton. This is possible only due to the weak force. Correct? So, that's all about your force. So, what we saw in the today's class is, so basically the types of force. In earlier class, we took it a different level. We found the inertial frames. And when we say for a non-inertial frame, the frame has to be accelerated. And what Newton's law says, if there is any acceleration, there has to be a force applied to it. So we know that. So then we came to come to a picture. Force is a fundamental quantity which is going to define a frame is an inertial or non-inertial frame. So any force which is acting it. So then when I put up the question, what are the types of force we observe in nature? Okay, so then we found out these forces can be derived into 4 fundamental forces and we discuss about this force. Okay, so in the next class, I don't know what is there in your next portion. They have written about the unification of forces. That's the Newton tried to, because they try to unify all the forces. Okay. Anyway, these two forces are unified. This Abdus Salam model is there. Okay. So then the contact and non-contact forces, real and pseudo forces. Anyway, we will see about it. There's the one problem. Next class we will see this problem first, and then we'll go to the rest of the portions. Okay. Okay. I'll stop.